So let's now see all of this in action. Well, here's some really nice data that was collected on an isokinetic dynamometer. And what you can see on the x-axis is you can see the knee angle. So you can see knee angle going from about 90 degrees to 0 degrees. And you can see that schematically. So you've got a 90-degree flexion in the little cartoon drawing up to full extension. And then what you've got is the amount of torque being produced in Newton meters. But what they've done is they've recorded this at 3 angular velocities. Okay, so 3 angular velocities. You've got 0 degrees, that is under isometric loading, 15 degrees per second, and 180 degrees per second. So what can we see? Well, if you look at the isometric loading, you are seeing pretty much what we were starting to think about previously within this video cast, which is the length tension relationship of the muscle. In fact, you're seeing it in all of them. But particularly if you look at the isometric, you can see that kind of inverted U. That when the muscle is elongated, so we've got a knee angle of about 15 degrees, there's very little force being, about 100 newtons of force is being produced. But actually, when they were getting to knee angles of about 75 to 60 degrees, they were producing about 225 newtons. And in fact, what you'd start to see, very hard to go beyond 90, but let's say they went to 100 degrees, you'd see the amount of force starting to reverse in the opposite direction. But you're also seeing that when the velocity of shortening is actually, you've got movement taking place here, and you can see the same thing. That when the velocity of shortening is, say, 15 degrees per second, you'll notice two things. The amount of force being produced at 15 degrees per second across the full range of motion is far greater than it is at 180 degrees per second. And this is fundamentally due to the time under tension. The more time the muscle is under tension, the greater the ability the muscle has to generate force. But also what you will see is that the angle where the peak force is being attained is different at 15 degrees per second, which is around about between 75 and 60 degrees, compared to at 180 degrees per second, where it's between 60 and 45 degrees per second. And this is fundamentally connecting the length tension relationship of the muscle with the force velocity relationship. You're connecting here Hemmelmann's size principle. Remember that in all of these is the maximal voluntary contractions, but also with rate coding. So what you're really seeing is what is happening at different velocities of shortening when we've got different speeds in terms of the amount of force being produced, which is not uniform. You've got that length tension relationship, but also that length tension relationship is fundamentally moved and shifted depending upon the velocity of shortening that's been undertaken. And if we look at this here, this is the same kind of data set. What you can see is, if we take, for example, let's take 75 degrees, so this is our kind of knee angle. So if we take 75 degrees as the knee angle, and then look at the different velocities of shortening. So if you say isometric, notice that isometric, they're producing 231 newtons. But if you go to 180 degrees per second, they're down to 83. And this is really important. Why? You're seeing the force velocity relationship. High force, low velocity. So velocity is 0 under isometric loading, force is high. Velocity is high at 180 degrees per second, therefore the amount of force we are able to produce is low. And you can see that across the board, whether it's at 75 degrees down to 15 degree knee angle, same thing applies. Okay, the knee angle might be 15 degrees, okay, but what you can see is that at 100, a velocity of shortening at 0, 100 newtons, 180 degrees per second, working across just a very small range of motion, we're down to 52 newtons. So big difference. So what you're seeing is the force-velocity relationship in action here. And you can just see this a little bit here. You can see our force velocity, which is A, and our power velocity B, which is very much what we were looking at earlier on. But it's, again, it's that force velocity relationship. And had those authors kind of measured power, in essence, what you would see is the panel on the left. And this is some data that we produced a number of years ago now, 2013. And it was in relation to menstrual function. That doesn't really matter that it's in relation to menstrual function. But what you can see is we've got data. This is knee extension and knee flexion. We've recorded it at 4 different velocities of shortening from 60 to 240 degrees per second in both the extensors and the flexors of the knee. But what you can see is the same thing. As the velocity of shortening increases, irrespective of the phase that you're looking at in the menstrual cycle, as the velocity of shortening increases, the amount of force being generated decreases. Force-velocity relationship. And it's fascinating actually to note that there were quite significant differences in relation to different phases of the menstrual cycle, which is an interesting concept. Why? Well, because fundamentally something we've not really had time to refer to today is about how fundamentally important in this process, particularly in the development of force, but also the sustainability of force, how fundamentally important hormones are, and in particular within our females, how fundamentally important progesterone is in this. And actually that what you get, of course, throughout the menstrual cycle are fluctuations in progesterone, and the fluctuations in progesterone have quite significant effects on the amount of force being produced. And you can see that quite clearly in menses. You can see quite clearly that the amount of force being produced, if you look at 60 degrees per second, is far lower than you're seeing both in mid-follicular, mid-luteal and pre-menses, as an example. And this nice bit of data here, again, is just to show you something which is about the understanding of transference of force. And so what you can see here is a really neat study where what they've done is they've measured force at different angular velocities pre and post a training intervention. Now, in panel A, the participants trained at an angular velocity of 100 degrees per second. That's all the training they did over the training intervention. The group in panel B did all their training at 250 degrees per second. So you've got a group training at slow angular velocities and a group training at high angular velocities. But what is really interesting is notice how this manifests itself. So the pre-training is the solid line, the post-training is the dashed line. And what you can see is that the group that trained at the slower angular velocities have a greater transference effect than those which train at higher angular velocities. You can see that. Why? Because in the 100 degrees per second group, they're getting improvements from isometric, 0, all the way to 250 degrees per second. They're all showing a significant increase. Whereas our group that trained at 250 degrees per second are only really getting improvements from about 150 to 250 degrees per second. Why? Well, the key here is to do with muscle morphology. That fundamentally the generation of force is linked, as we've been referring to the structure of the muscle fibre. And the structure of the muscle fibre is fundamental primarily in relation to slow generation of force and slow angular velocities. But it also must have a play in a part in terms of, it has to contribute. We need to have muscle architecture for high angular velocities. But high angular velocities are also fundamentally governed by neural recruitment. And so if you only train at high angular velocities, you fundamentally only ever train with very rapid velocities of movement. You're not getting enough time to generate in training the hypertrophic effect. And you need the hypertrophic effect to contribute to the slower angular velocities, to generate to have the muscle architecture to contribute to the more strength-based mechanisms. As the angular velocity increases, we're starting to get into more power-based mechanisms. And so the final thing to leave you with in this session is this, which is fundamentally what we've been dealing with today is everything you can see on the right-hand side of this panel, which is shortening. And that is the classic force-velocity relationship we've been referring to. High force, low velocity. Low force, high velocity. So you can see that quite clearly. And you can see the midline where you've got a score of force of about 2. That's an isometric contraction or isometric action. Why? Because the angular velocity is 0. But what about what's going on the left when the muscle is under stretch or lengthening? Notice that what's happening here is as the angular velocity increases, so does the amount of active force being produced. Well, how can that be the case? Well, it can be the case because what you're seeing is on the left is under eccentric loading, on the right is under concentric loading. So the classic force velocity curves we've been referring to only exist, as you see here with this exponential like that, under concentric loading. If it's eccentric loading, as the amount of the rate of force development increases, then the bigger the braking mechanism that needs to be applied increases. The amount of force we have to generate increases. Think about it very logically. If I'm running and I'm running really fast and I suddenly have to put the brakes on, I've got to decelerate far more than if I'm jogging slowly and put the brakes on. So what you get under eccentric loading is, as the velocity of shortening increases, the amount of force that we need to generate also increases. And this is fundamentally important to us as physiologists, because it actually ties into something really important. One, there's a large neural component in that, because you have to have high neural recruitment to get deceleration of forces. But two, concentric loading, as we've already been learning through the excitation contraction coupling, is an ATP dependent process. Eccentric loading is almost completely devoid of ATP regulation. There's almost no ATP involved. Why? Because in essence, the only ATP that is being used is at the point where you apply the braking. Throughout the rest of that range of the motion, most of that control is under neural regulation. There's very little ATP involved in the whole of that process. So it's really important to kind of understand that eccentric actions are so fundamentally important to sport, because they are very, very energy efficient. They're highly fatiguing, neurally highly fatiguing, but in terms of metabolic costs, very, very low.